All right, so let's pick back up where we left off with formal charge. Okay, so we talked a little bit about resonance structures yesterday. Nod with me, nod with me. Okay, so we talked about how sometimes there's more than one ways to draw things. But the resonance structures we drew were pretty similar, right? It's just maybe we moved a double bind, but overall the structure looked the exact same. Sometimes when we draw these things, they are not going to look the same. So we've got to figure out which one is the most plausible way to draw it. Okay, what way would be technically most correct? And so to do that, we have to look at the formal charge. Okay, so we have to look at the formal charge. So an atom's formal charge is equal to the group number. So that's just the regular number of valence electrons. Okay, just the regular number of valence electrons that an atom normally has, minus, let's change this around, the number of lone electrons that are assigned to it, plus 1/2 of the number of bonding electrons. Now, don't let this equation confuse you right now. We're going to get there. Okay, so there's the equation that we're going to use. Notice that the sum of the formal charges must equal an ion's charge. So if it's a neutral atom, then the sum of the formal charges has to equal 0. If it's a polyatomic ion, like we're going to do sulfate in just a minute, what's the charge of sulfate? 2 negative, okay? So since the charge of sulfate is 2 negative, when we add up the formal charges, it has to equal -2, okay? So that's how we're going to do it. How do we choose? If I'm looking at two different structures, how do I choose? Well, we want the formal charges to be as small as possible, okay? Which means we want them to be as close to 0 as we possibly can get them. Okay, sometimes there's no way to get it to be 0. We can't make it 0. So if that's the case, if we have a negative formal charge, we want to make sure that it's with the most electronegative atom in the molecule. Okay, can we look at the periodic table and decide which one's the most electronegative? Yes, we can. All right. So for the example, it says draw all possible structures for the sulfate ion. Decide which is the most plausible using formal charges. So again, what did we just say sulfate was? SO4 2 negative. So I'm going to come down here and do it so I've got more room to draw it since the smart board can be writing bigger than in your notes. So it's SO4 2 negative. Okay, how many valence electrons does sulfur have?
Sulfur has 6.
6. Plus how many does oxygen have?
6.
Now I have to multiply that times 4, and then that 2 negative means I have to do what? Add 2. Okay, so 6 plus 24 is 30, plus 2 is 32. And if I divide that by 2, I get 16. So I should have 16 pairs of electrons in this. So the first way I draw it is just the normal way. I put sulfur in the middle. I show all of the oxygens single bonded to it, and then I put the lone pairs around it on the outside. And then because it's a polyatomic ion, I have to do what? Put it in brackets and put the 2 negative on the outside. And so I double check myself. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 electron pairs. So is this a way that I could draw sulfate? Yes. There's another way I could draw sulfate though. If I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Now, why is it that sulfur can have more than 4 bonds on it?
Because 6 is okay.
Because it's in the what? The third period or greater. So I know that it can have 6. So we see that? Yes? Now, because I have 2 double bonds here and the single bonds here, is there another way I could draw this structure? Yes. I could put the double bonds on what? the top and bottom, and I could leave the single bond. So I've got to show that this is a resonance structure, where I could have my oxygens double bonded on the top and the bottom, and I could have my single bonds on the side. Now, is this first drawing the same as the last two?
No, it's got
No.
because it's got a double.
It's just got single bonds. But are these last two the same drawing? Yes. Okay, does everybody see that? All right, so now let's see. Which way is the better way to draw it? The first way that we drew it, or is it better to draw it using the two resonance structures? So to do that, we've got to do formal charge. Okay, so let's start with oxygen. Since all of these oxygens are the same, we just have to pick one. Okay, so I'm going to do this one right here. So I say, okay, how many valence electrons does oxygen have? 6, right? Because that's what it is on the periodic table. So I just write a 6. Minus, how many electrons does oxygen have to itself here? 6, right? 1, 2, 3, 4, 5, 6. Okay? And then we have to account for one that's being shared right here. So there's 2 of them right here, but only one of them we account for with oxygen. Okay? So that would be
Sub to sub to that. It was like, I don't even know what that is. I'm sorry.
Alright, sorry, Hopeful. Somebody came to the door. I'm back. Okay, so we've got 1, 2, 3, 4, 5, 6, and then remember we have to account for one of them that's being shared. So that would make it 7. Does everybody see that? So I count 1, 2, 3, 4, 5, 6, and I only count one of the shared. So there's 7. So 6 minus 7 is equal to what? -1. So the formal charge on every single one of these oxygens is -1. Does everybody see that? Yes. All right, so now let's do sulfur. Okay. How many valence electrons does sulfur normally have? 6. Minus, does sulfur have any on its own in this drawing? No. So I've only got to count for one of the ones that it shares. So 1, 2, 3, 4. So 6 minus 4 is equal to +2. So the formal charge on this sulfur is +2. So if I add up all the oxygens, what is their formal charge? -4 plus sulfur's is a +2. So overall, what is the charge of this? -2. So do we see how we come up with the charges on our polyatomic ions? Doesn't it though? I know.
Why couldn't y'all just explain this earlier?
This would have been so much easier.
It's another.
Yay! Okay. So here's one of them. Here's the first one. So now we've only got to do one of the resonance structures because they're the same, right? So we're just going to do this first one. So do we already know the charge on the single bonded oxygens?
Yes.
Yes, we've already did those in the other one, so we know both of those are -1. But is the charge going to change on the double bonded ones? Yes. So we look at the double bond and we say, okay, so I'm going to look at this one. Oxygen normally has how many valence electrons?
6.
6. Minus, how many does it have here? 1, 2, 3, 4. And then I've got to count what? 5, 6. I've got to count 1 for each of those bonds there. So 6 minus 6 is 0. So the charge on this one and this one is 0. So then I look at sulfur and I say, how many valence electrons does sulfur normally have? 6. Minus, does it have any on its own? No. So I just count for 1 of each of the bonds. 1, 2, 3, 4, 5, 6. 6 minus 6 is equal to, so the charge is there 0. So -1 plus -1 is -2. So which drawing is more plausible?
I assume it's gonna be the double bond.
They are both possible, but what did we say that we want the formal charges to be? As close to what as possible? 0. Which one of these drawings has more 0 formal charges in it? The second one. So these would be the most plausible drawing, not this one.
No, will they like knock us points if we do that one?
I don't know. I don't even know if they would do that to you on the exam. I think if they gave you something like this, it would be like obvious. They're asking you, okay, here are 2 structures, which one's more plausible? Does that make sense? I don't think that you would necessarily have to recognize that there's 2 different ways to draw it. Okay. So it's pretty straightforward. All right, everybody got that? Because I'm about to erase it. We're good?
Caution. What? I don't know.
All right. So the caution is these are only estimates. If we really honestly wanted to know the real true way to draw it, we would have to do an experiment. Just like everything else we always say in chemistry. The only true way to know how it's going to behave is if we do an experiment. Okay. All right, so biscuit or 2 slices of breakfast pizza, either one. All right. So now exercise 10 says give possible Lewis structures for XeO3, so xenon trioxide, an explosive compound of xenon. Which Lewis structure or structures are most appropriate according to the formal charges? Now I'm going to go ahead and give you a warning here. There are 8 possible structures you can draw if we drew all of the resonance structures. We're not. Okay, we're just going to draw the 4 possible ways, and you just need to recognize there are resonance structures. Okay, because that's a little much for anybody to draw. So the first way we could draw this is we could put xenon in the middle. We could single bond oxygens to them. Just gonna pull that door too. This second way we could draw this is we could double bond one of the oxygens. The second way we could draw this, the third way, is we could double bond 2 of the oxygens. And then the last way we could draw this is we could double bond all of the oxygens. I don't know, because that's what your book says. And I think it's because xenon is so low on the periodic table, it can form like multiple upon multiple bonds. Because it's got a lot of orbitals it can expand into. There's an assumption. All right, so let's do formal charges and pick out which one would be better. So let's start with the xenon on the first one. So how many valence electrons does it normally have? 8. Minus, how many are assigned just to it? 1, 2, 3, 4, 5. So 8 minus 5 is positive 3. Okay. I went 1, 2, and then you count 1 for each of the bonds. 3, 4, 5. Okay. So now let's look at oxygen since they're all the same. How many valence electrons does oxygen normally have? 6. Minus 1, 2, 3, 4, 5, 6, 7. It's negative 1. Now, is this a neutral molecule? Yes. So should my formal charges add up to 0? Yes. So I've got positive 3, negative 1, negative 1, negative 1, which would be what? 0. You see that?
How do you know it's a neutral?
Because it didn't have a charge on it when they gave it to me.
Oh,
So I know it's neutral. Okay. So we don't have anything to compare it to yet. We just know this does work. Right? Right. So now let's move on to the second one. I already know the single bonds are what? -1s, right? So now all I have to do is redo xenon and the double bonded oxygen. So xenon has how many valence electrons normally? 8 minus 1, 2, 3, 4, 5, 6. Does everybody see that? So that would give xenon a +2. And then this double bonded oxygen normally has 6 valence electrons. We count 1, 2, 3, 4, 5, 6. 0. Okay. So which one would be a better structure so far? The first one or the second one? The second one. Okay. So therefore, I can take the first one out of contention. Do we see that? Do we see why the second one's better?
I don't see.
Okay, because I have one of the oxygens that's at 0, which is what I want. I want them to all be as close to 0 as possible. And xenon is now at a +2 instead of a +3, so it's closer to 0. Okay?
So we're just trying to get closer to 0.
Trying to get close to 0. Alright, so let's look at the third drawing. I already know my single bonded oxygens are -1. My double bonded oxygens are 0 and 0, because we already figured that out, right? So now I just have to redo xenon. It normally has 8 valence electrons. I count up 1, 2, 3, 4, 5, 6, 7. 8 minus 7 is +1. So now which drawing is better, the second one or the third one?
Third.
The third one. So now it's between this one and this one. I know all of these oxygens are 0. So my xenon is equal to, there's normally 8. I count 1, 2, 3, 4, 5, 6, 7, 8. And so 8 minus 8 is 0. So which one's the best way to draw it?
Is it always going to be the one?
Yeah.
Not always, but double bonds. Remember, why do we like double bonds and triple bonds better than single bonds? They're stronger, okay? And so it decreases my bond length, so it increases my bond energy, it makes it more stable, it makes it stronger. So typically, yes, just because of that. Okay? But formal charge is not hard? No, we like formal charge. Yes, formal charge is a good thing. So now let's talk about our favorite. Okay, just kidding, my favorite. Maybe not our favorite. I shouldn't make that assumption. So let's talk about my favorite. Okay, molecular geometry. Love it. Love it, love it, love it. I don't know why.
Trigonal.
I just find it fun. It's not geometry though.
I know, it just says that.
It's not. Were those over
Yeah,
there? Oh, okay.
Trigonal.
I don't have orange in here though. I feel like those go in one of these and we need
No,
to
it
figure
doesn't
out which one it is.
I built this thing out of those.
Okay. Alright. So, molecular shape. Here's the deal. Vesper theory. We're going to use the Vesper theory for this. And you did this last year. Promise cross my heart you did. Okay?
It was just so hard.
Right.
I could not remember what was what.
You're going to be good. You've got this. Okay? So, this is the valence shell electron pair repulsion theory. Whoa. Okay, I know. You read that and you think, whoa, what in the world? Don't. Just remember, electron, if I put them close to each other, they do what? They repel. Okay? So that's literally all we're saying, is the fact that electrons repel each other is going to cause my molecule to change shapes. Okay? It's going to define the shape that the molecule is going to be. So don't let Vesper throw you off. It just means electrons repel, so it causes me to have different shapes. Okay? Now, we have electron geometry and we have molecular geometry. Now, we are going to focus a lot today on molecular geometry, but I want you to understand the difference, okay? Electronic geometry is kind of like, what does it look like when I draw the Lewis structure? Okay, when I draw it flat on paper, how does it look to me? Okay, versus the molecular geometry is, how is it going to look when I put it together in an actual molecule? Okay, and we're going to be able to predict both. Are you ready? Now, if it has a total of 2 bonds or a bond and a lone pair or anything like that, okay, then the electron geometry, we haven't gotten to molecular yet, okay? The electronic geometry says it should be linear. What's the base word of linear? Line. So we are assuming that it should just be in a line. Everybody see that? Okay. So when I first look at, if I drew H2O, what does it look like it should be in? A line. So if I asked you for the electronic geometry of that, you would say it is linear because it looks like it's in a line, right? Yes. Okay. Now, if there are 3 things bonded to it, or maybe 2 things and a long, you get what I'm saying, okay? Then we say that, oh, that's a bad thing. Don't ignore that one. I messed up. Yeah. It does, but that's still not. Because this is the number of bonds plus the number of lone pairs. So let's just go with, I can't think of anything. Oh, like if I had like HCO. Okay, there's only 1 bond. See that? So that is going to be linear.
Just plus the one here, so wouldn't that be 4?
No, because you don't count the lone pairs unless they're on the central atom. There's no central atom there. Okay, geez. Okay, that's a bad example too then, Zach. Here we go.
Yeah.
Okay, you don't count the lone pairs unless they're on the central atom. Okay, so here's the central atom. It's only bonded to 2 different atoms. There you go. That's linear.
Oh, yeah.
Is that better?
Yeah.
There we go. Did everybody see that? All right, so now we're going to assume that it's trigonal planar if we've got 3 things going on. Okay, so we've got a total of 3 things going on. Like VF3. Okay, I've got 1 central atom. How many bonds does it have going on? 3. Okay, so I would say according to the electronic geometry, that should be trigonal planar. Okay, because tri means what? 3. Everybody see that? Tetrahedral would be if I have 4 things going on. Okay, so that would be something like I could either have like maybe CH4, where I've got 4 bonds, or maybe I have something like NH3, where I've got 3 bonds, but I've also got a what? Lone pair. So do we see that? So that would be tetrahedral. This is just electron geometry. We haven't gotten to molecular geometry yet. Okay? Trigonal bipyramidal would be something like if I had PCl5. Now to me this one's easy because tri means 3, bi means 2, so 3 plus 2 is 5. So if I have 5 things going on, then I know it is trigonal bipyramidal. Do we see that? Okay. And then if we have 6 things bonded to it, and this is where it gets like, we say then it's octahedral. But octa means what? 8. That's because they say if you have 6 things bonded to something, it has 8 sides to it. Okay. Now we're gonna draw some today. So if y'all can figure out where the 8 sides are, please show me because I haven't found them yet. But people smarter than me say there's 8 sides. So that's what we go with. All right. So are you with me so far? Do we understand how we do the electron geometry? Now, it changes a little when we get to the molecular geometry. Okay? It is not the same as the structural geometry or the electron geometry. Okay? Why? Because lone pairs, okay, are going to cause a repulsion on the other things that are bonded to the nucleus. Okay? So it's going to cause them, we talked about this last year, it's going to cause the other molecules to be what? Pushed down. Okay? It's going to cause them to be bent. Okay? So, let's look at what we're talking about here. Those were the notes from last year.
I remember those.
You remember those? See? I know. We'll go back and look at them. I think I'm going to give you a copy of them Monday because it just has everything listed out instead of all jumbled like it is on here. All right, so let's talk about, first of all, about that tetrahedral. Okay, remember we said with the tetrahedral, it has 4 things on that central atom, whether it's 3 things in a lone pair or if it is 4 different things bonded to it, right? We just say it's tetrahedral. Well, it changes a little bit when we start putting lone pairs. Okay, so when we start putting lone pairs in here, notice what happened. When I drew NH3 earlier, I drew it like that, right? But when I look at the picture, What did this lone pair right here do to these hydrogen molecules?
Forced it down.
It forced them down. Okay? And so when it forces them down, we say the electron geometry is tetrahedral, right? Because I've got 1, 2, 3, 4. But the molecular geometry, the shape it's going to be, is trigonal pyramidal. Okay? Because if I drew it without the lone pair of electrons, I have 3 things bonded to it, so that's where I come up with what? Tri. But because they're being pushed down, it causes it to take the shape of a pyramid. Do we see that? Okay. So the molecular geometry would be trigonal pyramidal. Do we see this? Yes. Okay. Now, what if I have something where I have CH4? Okay. CH4 is still going to stay where I've got 4 things bonded to it. Okay. I'm still going to say that that's just tetrahedral.
Because it's not all.
Okay, because there's no lone pairs on it. So I'm going to say it's tetrahedral whether it asks me for the electron geometry or the molecular geometry. Okay. All right. Now, what if I have something like water? Okay. So what if I have something like water, where oxygen has 2 hydrogen molecules bonded to it, but it also has 2 what? Lone pairs. Okay. So what do those lone pairs do to those hydrogen molecules?
It pushes it
It pushes them down. So then, instead of them being in a line, they look what?
down.
Bent. So again, we would say there's 1, 2, 3, 4 things on that oxygen, right? So if I asked you for the electron geometry, you would say it was what?
It was tetrahedral.
Tetrahedral, because there's 4 things. But if I asked you for the shape, we ignore the fact that those lone pairs are there, and we just say, well, it would be in a line, but they made it go bent. So the molecular geometry is bent.
I thought it was going to be extravagant.
It's just bent. It's just bent.
This is why you love it.
Okay. Yeah.
So,
All right, now let's look at what happened to the bond angles. Okay, let's look at what happened to the bond angles. When I have 4 things bonded to it, what's the angle between all of them? 109.5. What happened when I add a lone pair up there? What happens to my bond angle?
it decreases to 107.
It decreases to 107 because that lone pair is causing these hydrogens to be what? Pushed down even more, right? And then look what happens when I add 2 lone pairs to my bond angle.
It decreases it.
It decreases it even more because now I'm pushing those hydrogens down even further. Do we see that?
Mm-hmm.
Yes? They like it. We got it. So, to determine the geometry, first thing, always sketch the Lewis dot structure. Okay? Do not skip the step where you sketch the Lewis dot structure first. Okay? Then the second thing, okay, is you can describe the structural pair or you can describe the electronic geometry. And we skip that step a lot where you describe the electronic geometry because most of the time it just asks you for the molecular. Okay? And then the third thing is you're going to assign the molecular geometry. And that says to ignore the lone pairs, but I find this a little difficult to do, so I'm just going to cross that out. Okay. I know it sounds complicated, but it's not. We're going to do this. Okay? Yes? We got this? Yes, sir. All right, so everybody voted in class today that they would rather skip straight to building them instead of doing the rest of the notes first. So we're going to build today, and we'll finish the rest of the notes Monday. Okay? Y'all good with that? You going to build molecules today? All right, I have enough of these kits to where all of you can have one. Well, I'm going to build in front of you in just a second, so hang tight. Okay, cool. Everybody can get one.
So we're gonna have them all.
Huh?
I got it.
Just use your own piece of paper. Or if you want to use your lab notebook, they're stacked up on my desk if you want it to be kept in something so you know you won't lose it. Okay. All right, guys, what you're going to want to do on your paper, whether this is in your notebook or whether it's on your own piece of paper, is you're going to want to have 5 different sections, okay? So you can do this, you may want to do it long ways or lengthwise, depending on how big you write. I don't really know, okay? So we're going to have the formula. Excuse me. Oh, what do you call this? This is called molecular shape and polarity.
I get less and less creative with it.
Yes.
Yeah.
I'm still really fun.
So you're going to have the formula, then we're going to do the Lewis dot structure. Dan, I feel like I should have put sketch and shape differently. In fact, I am. Then we'll predict the shape, and then we're going to sketch it, and then we're going to predict whether it's polar or non-polar. Now, if something is polar, what does that mean?
Doesn't share with it.
They're not sharing the electrons equally. And if something is non-polar, then that means everything is being shared equally. Okay. Now, let's talk just a second. Let me go back because I forgot to point this out. Okay, now, notice when they draw this, do you see how they used dash lines here? And then they used a dark line here and then just a straight up and down line there. Okay, that is because, let me build this right quick. Let me build it and then I'm going to have to go on camera so hope one can see it. Huh?
It's like Legos for nerds.
It is kind of like Lego parents, you're right. Okay. Alright, so here is the CH4 molecule. Okay? Does everybody see it? Because this is CH4 on the board, and then here's CH4 that I just built. I can't see if you can see it or not. Hopefully, can you see it? There we go. Okay. So, everybody got a good view of it? Everybody see what it looks like? Alright. I'm going to go back to the board right quick so you can see what it looks like on the board. Okay, so this dark line is to show that the hydrogen is coming out at you. Okay, the dash lines show that these hydrogens are coming back. They're going back. And then the line straight up just means that hydrogen's coming straight up. Do we see that? Okay, so that's how we sketch them to show what they look like 3D. Do we see that? So, dark lines mean they're coming straight out. Dash lines mean they're going backwards, and then we just use a single line to show it's just sitting straight up on top of the cardboard. Everybody got that?
So we make these.
No, you don't have to make it right now. We're about to start. Alright, so let's start with H2. Now, before we build it, we always have to do the Lewis structure first. So don't get too excited, because we always get real excited, okay? And those of you who are with me and who are building with me, these are your single bonds, the short ones. Short ones are single bonds. The long, flimsy ones we don't use till we start making double bonds, okay? So all you're using right now is the short ones. So, H2. How many valence electrons are in hydrogen? 1. I've got 2 of them. 1 times 2 is 2. 2 divided by 2 is 1. So how am I going to draw H2? Okay, with H going to H. Okay, why do I not have any valence electrons there? Because hydrogen can only have 2 valence electrons, so that gives them both 2. Okay, so what shape do we think this is going to be? Well, if we build it, hang on, let me flip back. But we'll just bear with me because we are, you know, trying this all fancy. Actually, let me see if I can do both of them at the same time. There we go. I can hold it there. What shape is this? It's linear. There you go. It's a line. So for the shape, I would just write linear. And then if I'm going to sketch it, is it going to look any different than my Lewis dot structure? No. I still just have hydrogen connected to hydrogen. So you don't have to draw that any differently. Is this polar or nonpolar? Nonpolar. How do I know it's nonpolar? There you go, because the electrons are all shared equally. Alright, now let's look at HBr. How many valence electrons does hydrogen have? One. Plus, how many does bromine have? 17. 7, thank you. Alright, so 1 plus 7 is 8. And 8 divided by 2 is 4. So therefore I'm going to show H going to BR. And what else should I do after that?
Put the dot.
Show the lone pairs around BR. Okay. Now, if I build this, okay, I have hydrogen to bromine. If you're confused about what they are, there's a sheet inside of it. Do you see where it says what they are? Oh. Okay. So, what shape does this look like? A line. So this is linear. So how am I going to sketch this? Same way I drew it. So is this polar or non-polar? It's polar. How do I know it's polar? They're not shared equally. Br is much more electronegative than hydrogen is. Alright. Next we are going to do H2O. So how many valence electrons does hydrogen have? 1. 1 times 2 plus 6 would be 8. 8 divided by 2 is 4.
I'm checking out what's everything. I mean, to
We're just doing a lab today. So you'll need to make up the lab with some way. So, right, it's 4. So, oxygen's going to go in the middle. And we already know, because we've drawn this 1,000 times in our lives, okay, that those lone pairs cause those hydrogens to do what? Bend down. But we're going to do it anyway so you can see it. So, oxygen's the red one. We're going to show 2 bonds because oxygen can only make 2 bonds. And when you put your hydrogen on there, I can see what shape is this. It was in a line, and then what happened? It became bent. Okay? So this is bent. So we would show the oxygen with the hydrogen being pushed down. Is this polar or non-polar?
It is non-polar.
It's polar. Polar. If there's lone pairs on that central atom, it's polar. Alright, the next one is NH3, ammonia. Nitrogen has how many valence electrons? 5. Hydrogen has 1. 1 times 3. So 5 plus 3 is 8. So we divide by 2 and we get 4. So we're going to put nitrogen in the middle. Show all the hydrogens on it, and then where's that extra pair gonna go?
And I thought,
On the nitrogen. So then we get nitrogen out. And we say, okay. So it's got 3 things bonded to it. So I know the geometry has to be what? Something that is,
no,
that's trigonal, right? So I know my shape has to be something that's trigonal because it's got 3 things bonded to it. Okay, now if I asked you for the electron geometry, what would you say? Mm-mm.
No, just kidding.
How many things are on this central atom? 1, 2, 3, 4. So if I asked you for the electron geometry, you'd say it was tetrahedral. But I'm asking you for the molecular shape. So then for the molecular shape, I look and say, okay, I've got 3 things bonded, so I know it's going to be trigonal. Okay, what's this lone pair doing to these hydrogens?
bending it down.
It's bending them down. So it makes it into the shape of a pyramid. So this is trigonal pyramidal. So if I was going to draw this, I've got the nitrogen. I'm going to show one of the hydrogens coming out. And 2 of the hydrogens are what? Coming back. And then you can show the lone pair or you cannot show the lone pair. Polar or non-polar?
Polar.
All right. We already did CH4, right?
No.
Y'all want to do CH4? We'll do CH4. How many valence electrons does carbon have?
It's
4. Plus hydrogen has 1 times 4, so 4 plus 4 is 8 divided by 2 is 4. So I've got both carbon. So then I'm going to build it. So the black one. All right, and then everybody should have got something that looks like this. Where you've got the hydrogen on top and 3 hydrogens on the bottom. All right, there's 4 things bonded to that central atom, so what's the shape? Tetrahedral. So then if I was going to draw it, I'm going to show 1 hydrogen coming out, 2 hydrogens coming back, and 1 hydrogen sitting out. And I really honestly, by the way, those of you wonder, I think the AP exam would be fine if you just did it like that. Okay? But what's the fun in that when you know the correct way to do it? Polar or non-polar? Non-polar. Everything is being shared. All you need to hear is everybody taking their hydrogen. Ooh, now we're about to get fancy with it. L O. Bye, y'all. Have fun in the check center. Nice. All right, now, so who has? I've got 3 different atoms. So how do I know who goes in the middle here? You just looking at me like I'm crazy. Okay, that's what we say. Okay. All right, no, but let's think about it. How many bonds can hydrogen make? 1. So I know it's got to be on the what? On the end. How many valence electrons does chlorine have? 7. So how many bonds is it wanting to make? Just 1. So who has to go in the middle? Oxygen. Because this is the only one that is willing to make 2 different bonds, right? Okay. How many valence electrons does hydrogen have? 1. Chlorine has 7, and oxygen has 6. So 1 plus 7 is 8, plus 6 is 14. Divided by 2 is 7. So I know I should have 7 pairs of electrons. Yes. I feel like we should be catching on to this and nothing else at this point. Lewis dot structures should be becoming repetitious. Okay. So then I should the oxygen to the chlorine to the hydrogen. And then the chlorine needs those. So I've got 1, 2, 3, 4, 5 drawn. So the other 2 must go on who? Oxygen. So that I'm going to build it. Alright, so there's my red oxygen in the middle, and then chlorine is green, and hydrogen is white. And what do I notice about my shape? It's bent, okay? It was in a line, but now it's bent. I drew it in a line, but now it's bent. How do I know that it's going to be bent? Here you go. Got the 2 lone pairs on the oxygen that are pushing them down.
When did it put it on CLR? Much lone pairs.
Nope, because it's terminal. The lone pairs on the terminal atoms, the atoms on the outside don't really affect it. It's just those electrons in the central atom. Those lone pairs is what affects the shape. Okay. And this one is polar. I know, y'all hated me last year for this. It was this simple. Y'all just made everything complicated.
And so I feel like everything's done now.
But it's really not. In fact, I used most of these same examples with you last year and pitched fits last year.
What if we run out of room?
Okay. Get a new system. Return over. Alright, so next, let's do CH3. NH2. Whoa! We just went crazy with it. Okay? Alright. Who are my central atoms going to be? Carbon and nitrogen, that's right. How many electrons does carbon have? 4. Plus, how many nitrogens do I have total in this? 5. Plus, how many valence electrons does nitrogen have? So 4 plus 5 is 9, plus 5 is 7. There's electrons here. So we've already said our carbon and our nitrogen should be in the middle. Okay. Now, here's a hint that's going to help you in drawing. Carbon never has lone pairs. Okay? Carbon is the promiscuous atom on the periodic table. Okay? So carbon never has lone pairs. It will form double bonds, triple bonds, however many bonds it has to form, so it doesn't have lone pairs. Okay? Everybody good on that? Yes. All right. So, what's going to be bonded to the carbon here? It's going to have how many hydrogens on it? 3. So it's got 1, 2, 3, 4 bonds. So then the other 2 hydrogens are going to be on nitrogen. So I've got 1, 2, 3, 4, 5, 6. I've got one more pair. Where's it going to go? Now it's time to build it. Now, you're going to have 2 different shapes on this because you have 2 different center atoms. Okay? So we're going to look at the shape around the carbon, and then we're also going to look at the shape around the nitrogen. You are. Okay. So go on your carbon to your nitrogen. Yes, we are. We're going to have 2 quizzes. All right. Does everybody have it drawn? It almost looks like a little doggy when you get finished. See the head? And then the back legs?
Those are like a little bouncy balloon dog on
Its head is yeah, well. It's not a very pretty doggy, but it's a doggy. Thank you. And thank you, sir. Alright, so when we do the electron geometry of this, we've got to first look at just what's bonded to carbon, okay? So you pretend like those 2 hydrogen aren't there on the nitrogen, okay? And you just look at carbon and we say, okay, what's the molecular geometry around carbon? Well, it's got how many things bonded to it? 1, 2, 3, 4. So that means what is the shape that has to be around the carbon? Tetrahedral. Okay, so we say around the carbon is tetrahedral. Now, if I look at my nitrogen, now I pretend like those hydrogen on the carbon aren't there, so I've got my center nitrogen, okay, and then I've got 1, 2, 3 things bonded to it, so I know it's got to be what? Trigonal, okay? So I know around the nitrogen it has to be trigonal. Now is it going to be trigonal planar or trigonal pyramidal? It's going to be pyramidal. How do I know it's going to be trigonal pyramidal? Because it's got that long pair there, so that means those hydrogen get bent, right? Now let's be adventurous.
Hey, we can understand.
No, let's be adventurous and see if we can draw this. Okay, so I'm going to show my carbon at the bottom with my hydrogen going out. This hydrogen going back. Attached to the nitrogen at the top. With these hydrogen going back. That's the way I do it. Like this. Technically like that is how I do it. Alright, take it apart.
So this one will be hollow.
Yes. No, this one will be colored. It's got that long hair. Alright, now, we're going to keep going on this, but what I want you to start doing is I want you to try to start predicting the shape before you build the molecule. And then you build the molecule to double check yourself. Why do I want you to predict the shape before you build the molecule? There you go. You're not going to have these on the AP exam. Okay? They're not gonna let you take your model kit in there and build them, okay? Now, I wish they would, that would be great. Can you imagine in the middle of the test, like breaking out your kit? Yeah, all you hear was the pop, 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 pop. All right, so we're gonna keep going, and so you can use, I want you to keep building them, because A, they're just fun to build, and they're fun to look at, but I want us to try to predict what shape they're gonna be without building it, okay? All right, so the next one we're going to do.
Will they ever ask us to like draw it when you have to draw them?
I don't think so. I really don't think so. I just wanted you to teach that because there are some college professors that do expect you to be able to do that. So I don't want you to get to college. Again, I'm trying to prepare you for the AP exam, but my real goal in life is just so you get to college and you ace it. That's what I want. I would be more proud of that, honestly. Is that good? Not anymore. Really great. All right, so the next one we're going to do is O2. Right, let's pause right here and upload these so they can get their notes on today.